before the lecture starts, I would like to give a short introduction about the speaker. So Professor Kumaran has earned his bachelor's in technology from IIT Madras and then PhD from Cornell University. And then he did a postdoctoral, as a postdoctoral researcher, he worked at University of California in Santa Barbara, and subsequently he joined IISC. His research in fluid mechanics is distinguished by rigorous mathematical analysis and groundbreaking experiments. He is best known for his pioneering work on transition of flexible wall channels, where he demonstrated that instability can occur even at zero Reynolds number due to the coupling between the fluid and the wall dynamics. This is in contrast to the rigid channels where transition occurs at a finite Reynolds number. His experimental studies have also shown that this instability significantly enhances mixing in microfluidic devices, enabling efficient lab-on-chip applications. And he has also contributed significantly to the theory of granular flows and have provided quantitative insights into geophysical and industrial transport processes. Professor Kumaran has also made significant advancements in understanding of complex fluids, including polymeric gels, and his outstanding research has been recognized with numerous prestigious awards, including the Shanti Swarup Bhatnagar Prize for Science and Technology, the Swarna Jayanti Fellowship, and the J.C. Bose Fellowship. He's also a fellow of various academies like the Indian National Science Academy, the Indian Academy of Sciences, the Indian National Academy of Engineering, and the World Academy of Sciences, and the American Physical Society APS. All these reflect his significant contributions to his research field. So with this, I would like Professor Rajesh, who is in the audience, to invite Professor Kumaran by giving a flower bouquet. Thank you. This is fine.
Okay.
Sir, ये mic
No, because he has to record it also.
जी इसलिए सर कॉलर माइक से बोलेंगे सर तो ये आपको दे दें सर ये भी दो माइक लगाना होगा
Okay. No, he's saying there's a color mic this as well.
No, that goes to the recording
sorry sir
Oh, okay.
You can use the color.
Okay.
No, not an issue.
Yeah. I can use the color mic?
yes
I can use this one?
yes sir but you also
Also? Okay. Then I'll use only that one. Otherwise there'll be interference. Yeah. Is this audible? Yeah. Okay, great. Thank you so much. I'd like to thank the director, Professor Patra, and the chair of the committee, Dr. Ramanathan, for inviting me here, and Professor Dinesh and the entire faculty of chemical engineering for making my stay memorable. This is my first visit to IIT BHU, but I have been to BHU before as a tourist, and one of the things you get to see is the museum. Usually everybody sees the museum when in places they visit, but nobody sees the museum at their own place. And if you actually go there, you get to see what effort it took to put this, to start this place in the first place, you know. And particularly memorable was, I don't know, it's a 1 anna or half anna coin given to Mr. Malviya by a beggar on the street when he went around asking for alms to build up this university. And this university has had inspirational beginnings, and I'm sure it will continue to inspire all of us. So today I'll talk to you about transition to turbulence, and As with anything, this work is done by a large number of people, but unfortunately only one person gets to talk about it. So I should first acknowledge those who actually did the work, and also funding from Department of Science and Technology, Government of India over the years. What I'll try to accomplish today is to say a small number of things, okay, that fluid transition from laminar to turbulent flow is probably the most unsolved problem in physics, more than a century after its discovery. We still do not understand well the distinction between laminar and turbulent flows, and I'll try to tell you why it is difficult to understand, but more importantly, why it is essential for life as we know it. There are some flows for which we understand that the transition starts from an instability, and there are certain routes to turbulence. But for flows that are common every day, the transition in pipe flows, for example, is still poorly understood. Okay? And there are reasons for these, and I'll go through that. More as a motivation for you to join in and try to solve this difficult problem in your own ways. And I'll discuss some of our work at the end. So transition is something we see every day. We see it, when you open a tap, in the top there is a nice laminar flow with smooth streamlines, and at some point it breaks up into a turbulent flow. And if you open it further, you see that the flow is chaotic with velocity fluctuations in all directions. And this transition happens spontaneously. There's no need for there is need for an external disturbance, but there's no need for a continuous disturbance to generate a turbulent flow. Okay? And you see it in water, you will see it in air as well. At low velocities, the smoke is like a straight wisp, and then it breaks up into turbulence. Okay? And it's seen in all large structures. Okay? So I'll try to explain laminar and turbulent flows and what is turbulence and why do we have turbulence. Okay? Turbulence has various characteristics. Okay? It happens primarily at high velocities. It's called the Reynolds number, and it's highly irregular. The point is that turbulence is still a continuum phenomenon in the sense that you do not need a molecular description to get turbulence. Okay? So the smallest scales in turbulence are still much larger than the molecular scale. Okay? And it's highly dissipative and highly diffusive. I'll try to illustrate that. Okay? So high velocity. Okay? So the velocity is expressed in a scaled manner. Okay? For those who are not familiar with the field. The velocity, it's got a little cutoff at the bottom. It is the force exerted. So if you take two plates and shear them past each other, the force exerted is directly proportional to the area, inversely proportional to the separation, and directly proportional to the velocity. Okay? And if you write a force per unit area, it has a constant times the velocity divided by the length. Okay? The velocity divided by the length is called the strain rate, and this coefficient is called the coefficient of viscosity. And using this coefficient of viscosity, you can make a dimensionless group, which is called the Reynolds number. And when this exceeds some critical value, you get a transition to turbulence. Okay? And this is shown here by these experiments by Reynolds many years ago, where you see that at low velocities, you get a nice straight line. At some point, there is a discontinuous transition to a highly turbulent state. These are some pictures that we took in our setup that show the same thing. Okay? The transition Reynolds number is usually in the range of 10 power 3 to 10 power 4 in most situations. It depends upon the configuration, okay? But in all cases, you will get a transition from a laminar state at low Reynolds number to a turbulent state at high Reynolds number. Okay? And in our everyday life, we encounter things of various Reynolds numbers. Okay? So starting from the large scale, cyclones going at 10 kilometers diameter and about 160 kilometers per hour. They have a Reynolds number of about 10 power 10 or so. Okay? Clouds and river, etc., have about 10 power 7, 10 power 8. What we usually encounter in airplanes is about 1 million or so. And then smaller things have smaller Reynolds numbers. If you walk around the room, the Reynolds number is about 10 power 5. Okay? Right now, as all of you are sitting, there is, because of the temperature difference between your body and the surroundings, there is a thermal plume that is rising over your heads, which you cannot see because it does not interfere with light of any frequency. But if that plume did not exist, then your body would not cool as fast, and you would not be able to do thermal management of your own body by physiology. Okay? Similarly, human walking, birds have 10 power 4 to 10 power 3. Stirring sugar in a teacup, okay, 10 power 3. Okay? Insects have 10 power 2 to 10 power 3, and then we come down. Okay? Dust is smaller than 1, sand is about 1, and then blood flow is 10 power minus 2 in the smallest capillaries, and cell migration is still small. Okay? So these are the range of things that we see. Okay? So cyclone extending over 10 kilometers has a Reynolds number about 10 power 10. The clouds that you see around are about 10 power 8. River is about 10 power 7. Airplanes, 10 power 6. Okay? Most of you would have been in an airplane. What you would not realize is that this is causing structures that are much larger than the plane itself, okay, when it flies. Okay? And there are still smaller structures and so on. This is a visualization of a plane on the ground for research purposes. And it is because of this that airplanes, once one airplane takes off, you have to wait for some 2 or 3 minutes before the next one takes off. Because the turbulence that is generated by the previous one can significantly affect the safety of the one that follows. Okay? So this is smoke. And those of you who can see, you will see that there are smaller and smaller structures in all of these. Okay? So it's not just one large flow, you're seeing smaller and smaller flows within this. Okay? Similarly, in human walking, okay, as you walk around, you're generating a turbulent flow. Okay? Birds. Okay? This is for blood flow, cardiovascular flows. In the largest aorta, it's about 10 power 3 to 10 power 4. And this is a very good indicator of cardiac health, for example. They make it out by the sounds that are generated as the blood is flowing through. And there are certain sounds that are signature of turbulent flows. Okay? So stirring in a teacup, and then down to insects and so on, okay? Down to cell migration. And all the red are actually turbulent flows. Anything that is about our size or larger will be mostly a turbulent flow, unless the fluid is very viscous and so on. Things that are much smaller than us are typically laminar flows. Okay? And then there are transitional flows over here, okay, which are important for a reason I'll come back to. Okay? So it's highly irregular. Okay? So you can see that there is a range of eddies in this. Okay? As I showed you with the smokestack, there are large scale structures and there are smaller scale and smaller scale still. This has been realized for some time now. Okay? If you actually, Da Vinci was probably the first one to put it in words. Okay? Where is turbulence in water generated? Where does the turbulence in water persist? Okay? Where does it come from? And you can see the paintings that he drew, you can see smaller and smaller structures in these paintings, okay, drawn in the 1500s. Okay? And there is a theory due to Kolmogorov which says that the smallest scale in a turbulent flow goes as the Reynolds number to the minus 3/4 power times the large scale. Okay? And what that implies is that if you do this calculation, RE power minus 3/4 times the larger scale, which is about 10 kilometers, you get a small scale that's about less than a millimeter. Okay? So in that large cyclone that is swirling around, extending over tens of kilometers, the smallest little eddy of fluid that is actually present is actually less than a millimeter. Okay? And this smaller scale is remarkably insensitive to what the large scale flow is. Okay? So it's roughly 0.03 to 0.3 millimeters, regardless of the large scale flow, whether the Reynolds number is 10 power 5 or 10 power 10. Okay? Okay? And that is important. Okay? So the flow organizes itself in such a way that the smaller scales are roughly the same length scale. Okay? However, this 0.3 millimeters is still much larger than the molecular scale, okay? What I was telling you in the beginning. Therefore, turbulence is actually a continuum phenomenon. Okay? It can be well described by continuum equations. Okay? You do not need a molecular description. But requires a statistical description. Okay? So let me try to explain that. Okay? So if you write down the Navier-Stokes equations for any complicated shape, complicated flow, right? So you would think that you can just take the average of these equations to get an equation for the average velocity. Okay? That is not true. Okay? So we can do these simulations even for very complicated system, but we still cannot get a description. Okay? And the reason is the following. Okay? So this is for a, so let me try to explain that. Our simulations can actually bring out very, very sensitive features, okay, down to very small scales. Okay? But the question is whether being able to simulate something is the same as understanding it. Okay? And in the case of turbulence, it is not, because, and the reason is as follows. Okay? So simplistically, you would think that, they have some fluctuating velocity at some location. I can separate it into mean part plus a velocity fluctuation. The average of this fluctuation is equal to 0. Okay? So then I know what the equations are. They are continuum equations. These are well established. And I can think of just taking the average of this equation, take the average of this equation, get an equation for the mean velocity, and just go ahead and solve it. Okay? Doesn't work out. The reason is because you have this term here that is the quadratic in the velocity. Okay? If you have a fluctuating quantity, the average of the fluctuating quantity is 0. Okay? But if you try to take the square of the average, that is positive. Okay? So that is non-zero. Okay? So even though the average of a quantity may be 0, or the average of two quantities may be 0, if you multiply the two, that average is not 0. Okay? So the fluctuations actually enter into the equations for the mean flow. Okay? That is the fundamental problem of turbulence. Okay? It's called the problem of closure. Okay? You cannot close the equations at any stage. Okay? So if you cannot close the equations at any stage, then you're left with trying to make some models for these nonlinear terms. Okay? And it turns out that nobody has been able to figure out a general model. Okay? You can have specific models for specific flows, but you cannot get a general model that will work for all flows. Okay? That is the turbulence problem. Okay? And this has been realized all through history. Okay? I put some quotes here from very old quotes. I had less difficulty discovery of motion of heavy bodies in spite of their distances than the investigation of the movement of water before my own eyes. Okay? He's basically telling that the turbulent flow of water cannot be described by equations as cleanly as the motion of planetary bodies. Okay? And there is this quote due to Heisenberg. When I meet God, I will ask him two questions: why relativity and why turbulence? And I really believe he will have an answer for the first. Okay? And this has a history to it. So it turns out that for his PhD thesis, Heisenberg actually worked on the instability of a pipe flow. Okay? And he actually got the wrong answer. Okay? For those who know, he did what was called a long wave analysis, whereas the instability is actually at finite wave number. Okay? So he got the wrong answer. And so he decided to do something simpler, so he went and discovered the uncertainty principle. Okay? But till the end of his life, he never solved this. Okay? And you may have heard about the textbook of Lamb. He said something very similar to Heisenberg. Okay? So he talked about quantum electrodynamics as the one problem that he would like to see solved, and turbulent motion as the second problem. And about the former, I am rather optimistic. And this was actually remarkably prescient, forward-thinking, because in the 1950s, the problem of quantum electrodynamics was almost completely solved by Schwinger and Feynman. But the motion of turbulent flows of physics is still not solved. Okay? And those of you who studied physics from Feynman lectures, everybody reads the chapters. Not many people read the preface, but if you do read that, he says there actually that finally there is a physical problem that is common to many fields, very old, not been solved. Nobody in physics has really been able to analyze it mathematically satisfactorily, in spite of its importance to sister sciences. It is the analysis of the circulating or turbulent flows. Okay? And this is there in the foreword of the book. Okay? So, and then of course in the rest of the book he doesn't talk about turbulent flows at all. Okay? So so I said that there's a range of length scales for motion in a turbulent flow, all the way from the large scale spanning the system down to smaller, 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 and so on. And the smallest scale was the estimate I'd given you by Kumlakarov. It is not exact, but it's a scaling estimate. Okay? And that shows you that the small scale could in many cases be 5 orders, 6 orders, or 8 orders of magnitude smaller than the large scales in a turbulent flow. Okay? And what is happening is that energy is being fed in, okay, due to whatever was generating the flow. In a cyclone, for example, that will be the pressure difference that is generating the flow at the large scales, and then it is transmitted through a series of length scales down to the small scales until it reaches a scale where the Reynolds number based upon this scale is roughly order 1, so that inertial and viscous effects are comparable, and there it gets dissipated. Okay? So that is the basic principle of a turbulent flow. Okay? And we can get kinetic energy and dissipation rate and so on. We can get estimates of these as a function of length scale. Okay? And the idea here is that the smallest length and velocity scales do not depend upon the configuration of the velocity at the large scales, but only on the energy dissipation rate and the kinematic viscosity. So basically, if I have a flow and I make the fluid more viscous, the small scales will become still smaller. Okay? So that's the idea of a turbulent flow. This does not, so basically turbulence is a flow property. Okay? It's not a material property like viscosity and so on. And that is what is making the problem complex, because if it is a flow property, then it will be different for each kind of flow. Okay? So you cannot take what you learned from one kind of flow and apply it directly to another. Okay? So that is where the problem is. Okay? And this energy cascade has been seen. Okay? So Da Vinci himself said that smallest eddies are almost numberless, and large things are rotated only by large eddies and not by small ones, and small things are turned by small eddies and large. Basically, in 1500, he is saying that the large scales generate the energy, and then that goes through the small scales. Okay, just by looking at a turbulent flow. Okay, they didn't have the mathematics at that time to do anything, but just by looking at it. So it's a remarkable observation, and it sort of highlights the importance of observing things in solitude. Okay, instead of running around trying to write equations or do an experiment. Okay, that's where the thought process starts. Okay, and there have even been poems composed by Richardson on this. Okay, Richardson is the one who gave the mechanism for the large scale flow in the Earth's atmosphere. Okay, and it's also highly dissipative. Okay, so the dissipation rate in a turbulent flow is much higher than what it would be in a laminar flow for the same flow configuration. And that is the reason that for pumping of fluids and so on, we require much higher energy than you would simplistically calculate from a laminar flow. Okay? The energy requirement can be 2-3 orders of magnitude higher. Okay? But it's also highly diffusive. Okay? And it is for this reason that it is extremely important. Okay? So let me explain that. Molecular diffusion is due to the random fluctuating velocities of the molecules, the thermal velocities, which depend upon equipartition of energy. It's square root of kT by m is the molecular fluctuating velocity. It's also the velocity at which, in gases sound will transmit and so on. It's roughly the same velocity. Okay? So diffusion takes place because a molecule is randomly moving within a fluid, and if you wait long enough, it will sample all of the space. Okay? In contrast to a solid where molecules vibrate about fixed positions. And this molecular diffusion coefficient, it has dimensions of length square per unit time, because it's the distance square divided by time. The distance it travels, if it were going in a straight line, the distance would be proportional to time. If it is diffusing, the distance is proportional to t to the half, t power half. Okay? It goes as square root of time. Okay? The ratio of distance squared divided by time is the diffusion coefficient. Okay? And it scales roughly as the speed of sound times the microscopic scale. Okay? Molecular speed times the persistent length of motion. Okay? And you can calculate this. Okay? So for air, it is about 10 power, I'm sorry, this is cut off. For air, it's about 10 power minus 5 meters square per second. Water, it's about 10 power minus 9. Okay? So these are important numbers. Kindly just keep it in mind. For air, the diffusion coefficient is 10 power minus 5 meters square per second. For water, it's about 10 power minus 9 meters square per second. Okay? So, mixing by diffusion. Okay? So, how long would it take for something to mix? If you waited for diffusive transport to mix something. Okay? So, 2 into 10 power minus 5 is the diffusion coefficient in air. Water is about 10 power minus 9. So, if you put some sugar into your cup, diameter of about 4 centimeters, and wait for it to mix, you can just do this calculation. Length squared divided by diffusion coefficient is a time. That's about 10 power 6 seconds. Okay? So if you wanted to wait only for diffusion, it would take you about a week for your cup of sugar to mix in your coffee, okay, or tea. And similarly, the thermal diffusion time is about 10 power minus 7 meters square per second. So if you wanted to cook something in a vessel, and if you relied only on diffusion to do it, it would take you about 7 to 8 hours to be able to do it. Okay? And we cannot, of course, wait that long. So that is why turbulence comes in. Okay? So in turbulence, the diffusion time depends upon the eddy length scale and the eddy velocity, not the molecular length scale and the molecular velocity. Okay? And for a cloud, for example, Reynolds number is 10 power 8, and this is about 500 meters. Okay, and that is the reason the diffusion time, if you waited for molecular diffusion, you would take about 2.5 to 10 power 10 seconds for the moisture in a cloud to mix and seed and so on and create raindrops. Because of turbulence, it happens about 10 power 2 seconds, okay, about a minute or so. Okay, and that is the reason that clouds form over a reasonable time scale so that we get rain and then we can, grow our crops and all that kind of stuff. Okay. Similarly, if you waited for mixing in a river, it would take about 10 power 10 seconds, okay, whereas it takes about 100 seconds for it to mix over here. Similarly, for smokestacks, okay, 10 power 5 seconds is what it would take, and 10 power 3 seconds is what it would take for human movement, whereas this is about 10 power minus 2 seconds. Sorry, 10 power minus 1 seconds. Okay. So mixing at large scales takes place primarily because of turbulence. If you were to wait for molecular diffusion to mix things, then we would not see processes as we know them. Okay? And that is probably an anthropocentric answer to this question. Why turbulence? Because life as we know it requires turbulence at the large scales. Okay? Let me give you some examples. Okay? So before giving you some examples, I'll just discuss hydrodynamic stability and how do we detect turbulence. Okay? So the point is that if you have a flow in a pipe, for example, okay, it's a laminar flow, okay, and it spontaneously undergoes a transition to a turbulent flow. Okay? It is not that the laminar flow is not a solution of the equations when you increase the Reynolds number. Laminar flow is still a solution of the equations. However, any small disturbance and the flow will not return back to a laminar flow, it will go to some other state. Okay, so you can maintain a pipe flow in a laminar state at very high Reynolds numbers, even 10 power 10 and so on. But if there was a small disturbance, it will automatically transition to a turbulent state. Okay, something like this over here. Okay, so you can consider this as under gravity or a potential well or something. In this case, if you disturb it a little bit, it comes back. In this case, it goes unstable, okay, if you disturb it. Okay. And we detect this by doing what is called a hydrodynamic stability calculation. Many faculty here have done fine calculations on hydrodynamic stability in various contexts. Normally, we use what is called a normal mode analysis. That is, we expand this disturbance in terms of a series of disturbances, which we know can be summed up or linearly superposed to get a disturbance of any shape. Okay? And then we examine to each one of these disturbances, and if any one of them is unstable, then we know that the transition has taken place. Okay? So that is the kind of thing that is done, for example, for heating from below. Okay? The reason you're able to cook food is because when you heat from below, the fluid at the bottom is hotter, top is colder. So the bottom, because it's hotter, it is lighter. Top, because it is hotter, it's heavier. So you have a heavier density, a higher density on top of a lower density. That is unstable because if you reverse two volumes of fluid, you will get a net decrease in the energy. Okay? Because the heavier fluid has come down and the lighter fluid has gone up. Okay? And because of that, you get spontaneous convection rolls. And you can see these over here. You heat it further, it becomes turbulent. And that is what you see as boiling and so on in a vessel. And this is the reason you're able to cook in 15 minutes, 20 minutes. Whereas if you waited for heat conduction, it would take you many hours, half a day, something like that. Okay. And this is also important in the atmosphere. Okay, so the reason is because in the lower atmosphere, the temperature actually decreases with height. Okay, so you have hotter fluid below, you have colder fluid above. Hotter fluid has a higher density, the air, and colder fluid, the air above, has a lower density. And because of this inverse gradient in temperature right over here, okay, that is why you spontaneously get circulation patterns that happen. Okay, and these are responsible for formation of clouds and so on. Okay, those who have gone in a plane, you'll know that they go up to a height of about 3,200 feet, and they'll announce that we are flying at 32 or 2,900, something like that. The reason they do that is because at this particular height, there is no longer a reverse gradient. Okay, the temperature beyond this point it increases. That is stable, and therefore you have less turbulence over there. So they fly above the turbulence by going to a height where the temperature decrease stops, and then the temperature starts increasing again. But this temperature decrease is actually important for all the formation of clouds and so on. Okay, because without that circulation from the oceans, you won't be able to get clouds. Okay, and at that height of 3,200 feet is where all the clouds are. If you go slightly higher, the gradient is the other way. Okay, so so it's stable. Okay, so that's why you fly above clouds. Okay, because below clouds you have a turbulent flow. Okay, and without this temperature inversion and without the hydrodynamic instability, you would not have processes that make the temperatures around us reasonably comfortable. Okay? I mean, of course, it does get very hot and very cold and so on, but without the circulation pattern, it would be much hotter and much colder than it is today. And similarly, for rotating fluids, it's a similar thing. Okay? It's called the Taylor-Coet instability. When you rotate an inner cylinder faster than an outer cylinder, okay, so that the velocity inside is higher than the velocity outside, that is unstable because if you interchange two parcels of fluid, the centrifugal energy decreases. Okay? And because of that, this undergoes a spontaneous transition to form circulation rolls. Okay? You get rolls that look like this. And this mechanism is also responsible for the circulation pattern in the atmosphere. Okay, these circulations that you see in the atmosphere, okay, which transfer energy from lower to higher latitudes and vice versa, they depend upon this instability, okay, and the turbulent flow at the large scales. Okay, and that is the reason the Earth's atmosphere is so favorable for us. Okay, so I've given you some examples of why we depend upon turbulence, and those were cases like the Taylor-Coet and Rayleigh-Bernard instability, where we could actually predict it using a hydrodynamic stability analysis. These are cases where we still do not know how to predict it. These look simpler. They are like channel flows and pipe flows, but we still do not have a way of theoretically predicting turbulence in these cases. Okay? Part of the reason is because I told you that there's a transition that takes place, okay, where it goes from this kind of a behavior to this kind of a behavior. So if I put a disturbance of amplitude greater than this value, any small disturbance, it will spontaneously grow to this other state. Okay? And then the landscape further evolves. Okay? So if I put an amplitude of disturbance, I'll go to some other state. Okay? These are cases where that is not valid. Okay? So it goes from something like this to something like this. Okay? And if you put an infinitesimal displacement, you will see that it will come back to the same state. So you'll predict that it is laminar. But actually, if you put a disturbance with amplitude larger than a certain value, then it goes to some other state. Okay? So it looks something like this. It's called a subcritical transition. Okay? And that is the reason that the turbulent flow in a channel is still not predicted. Okay? So the landscape sort of looks something like this. You get this kind of a behavior for Rayleigh-Bernard and Taylor-Coet instabilities. But actually, for a channel flow, you never get this state. Okay? You get to this state and this state, but you never get to this state. Okay? And therefore, for a channel flow, the best experiments, theoretical predictions give you a Reynolds number of about 5,700. Experiments repeatedly show that its transition takes place at 1,200. Okay? And this discrepancy has never been satisfactorily explained. Okay? The best explanation we have so far is that there is a transition boundary that extends all the way to 1,200, and any small disturbance in the experiment will reach you to this turbulent state. The situation is worse actually for a pipe flow. Okay? Analysis predicts that the flow is always stable. Okay? Yet repeatedly we get transition to an unstable flow at a Reynolds number of about 2,100. Okay? And the transition is considered to be due to finite amplitude disturbances. And we can maintain flow in the laminar flow even at 10 power 5 if you take care to dampen out disturbances. Okay? So that is the situation for a pipe flow. Okay? And this is actually from Feynman's book. Okay? So he said the simplest form of the problem is to take a pipe that is very long and push water through it at high speed. We ask to push a given amount of water through the pipe, how much pressure is needed. Okay? And then he says, that is the central problem which we ought to solve someday, and we have not. Okay? So this has been recognized for a long time. But we can get reasonable results by just simulating the whole thing. Okay? Now computational resources have advanced sufficiently that we can just simulate the whole thing for reasonable values of the Reynolds number. Not for the very large scale, but for reasonable values of the Reynolds number. But then, simulation is not the same as understanding. Okay? And the central problems still remain. Okay? Okay. So as I said, we see turbulence at the very large scales. And this has been used in practical applications. Okay? The classic example is this Trans-Alaska pipeline, which goes for 1,200 square feet, 1,200 feet and 4 feet in diameter. And to actually reduce turbulence drag, they add about 2 million barrels of oil per day goes through. and they add small amounts of polymer, and that can reduce drag by about 40%. Okay? So by just trial and error, we know a fair number of things about turbulence, but we don't have a central answer to the phenomenon itself. Okay, so I'll just touch upon a few things that we did in this field. Soft channels and tubes is an area that I worked on for some time. As you can see, these are present in cardiovascular flows and so on. They are also present in small scale systems, microfluidic systems that are used in, for example, point of care diagnostics. And the question that we were asking, so I show an example here. So this is an example that appeared on the cover of Science, and you can see that there are many streams of different colors that come together. And over this distance of about 1 millimeter or so, you can see they don't mix at all. Okay? You can see the colors separately. Okay? And there's a clear distinction. Okay? And this is easily explained. Okay? The reason is mixing time is very long. So if I take the mixing times as length square by diameter, by diffusion coefficient is 10 power minus 9 meters square per second. If you take the length as 1 millimeter, you get a time of 1,000 seconds. Okay, so it takes a very long time to mix. And this is actually a technological barrier for these point-of-care devices. A typical device you will see will have a long path length for the reagents. Sample is put somewhere here, and it goes through long tortuous paths and mixes over here, and then goes again through long tortuous paths and so on. And even though this thing is itself just the size of a credit card or so, the total length of channel that it goes through is of the order of tens of centimeters to a meter. And the reason you require that long channel is because you have to wait sufficient time for it to mix by molecular diffusion. Okay? But there's a cost to be paid, and that is that you have to apply an extremely large pressure drop. And this is one of the things that is preventing the actual commercialization of these kinds of devices. Okay? Because the pressure drop required for laminar mixing by diffusion over long channel lengths is first of all, it's prohibitively high, and secondly, there's a significant chance of failure, mechanical failure, simply because you're applying such a large pressure drop. Okay? So one of the things we were looking at was that rather than having a rigid surface, can we put some kind of a soft material? Okay? And if you put a soft material, for those who have done some basic dimensional analysis, there is one other dimensionless parameter that enters into the problem. And so a transition has to be a function of these two. Okay? These are soft materials with elasticity about 10 power 4 to 10 power 5 pascals. Okay. So I'm going the other way. Yeah. Okay. So our analysis actually showed that this transition is actually due to a linear instability, whereas the transition in a pipe, I told you, cannot be captured by a linear stability analysis, okay, because it is highly subcritical. This turned out to be that a linear stability analysis can capture. Okay, so we had obtained analytical results in different regimes and numerical results in intermediate regime and so on. Okay, and we found a range of instabilities. I show the two parameters here, the Reynolds number and sigma. This is the transition in a channel at 1200, okay, for the rigid surface. And we saw instabilities going all the way to much lower Reynolds numbers, okay, subcritical instabilities in some cases. And the mechanism was different. Okay, so the mechanism was different. The mechanism was that if you deform the interface, right, the shear velocity at the crest and the shear velocity at the trough are different. Okay, and that difference in the shear velocity exerts a torque that tends to destabilize the surface. This mechanism is not present in the case of a rigid tube because you cannot deform it. Okay, so you have mechanisms of instability that are qualitatively different from what you would have in a rigid tube. Putting a soft surface is not just a quantitative modification of the rigid tube instability. Okay, so is that seen in experiments? Okay, so we fabricated some experiments. These are once again at very small scales. So I told you in the beginning that flows that are our size are turbulent and flows that are much smaller than us are laminar. Okay, so the question was to see how low can we go, where can we trigger a transition to turbulence to enhance mixing in these kinds of small scale devices. Okay, and so this was a channel with, we had made a shear modulus of about 55 megapascals on 3 walls and made the 4th wall very soft. And this channel was a sort of a bore, a rectangular bore within this gel block. And the width was about 1.5 or 1 millimeter. And the smallest dimension, which was the height, was 100 microns. Okay? So 100 microns is actually the thickness of human hair. Okay? So that is the dimension of this, that is the size of the smallest dimension. Okay? and we had inserted fluid at two ends, and then there was a development section where all four walls were made of rigid material, and then a test section where we made one of the walls made of soft material. And this is what we see. So if we inject, for example, black dye on one side and clear fluid on the other side, you see that initially it is laminar throughout. There is no mixing between the two streams of fluid. And when you go to a Reynolds number of about 200, you see there is intense mixing across. Okay? And this is over a channel that's about 3 centimeters in length, about 1.5 millimeters in width, and 100 microns in height. Okay? At a Reynolds number, which is 200, whereas for the rigid channel, the transition Reynolds number is about 1200 or so. Okay? And then we compared experiments and theory, and the experimental points were over here. This is the rigid channel transition, and our theory predicted this. Okay? So you can see that there is a difference by an order of magnitude or so in this. Okay? And this happens, whenever you compare experiments and theory, this kind of a thing happens. So then you have to go back and try to figure out why there's a discrepancy. Okay? And the discrepancy was because we had assumed in theoretical analysis, like all good theoreticians, that channel was rectangular and the flow was parabolic and the channel walls did not deform. Whereas when you go to apply a pressure drop across a soft gel wall, you can see there's significant deformation, okay, at the bottom. Okay? And so you have to go back and redo the calculations. So we got the shape of the channel from the experiments and created it in simulation software with cross-section at different locations. And what you find is that the flow is no longer parabolic. Okay? The flow varies with downstream distance. Pressure gradient is no longer linear as it would be for a laminar flow. There's a sharp drop at the expansion region, and then there is a slow decrease further down. Okay? And if you put all this together and once again do the linear stability analysis, you find that we use the local velocity profile and pressure gradient and parallel flow approximation. The instability is first predicted at the downstream converging section, not at the upstream diverging section. That is what you actually saw in the experiments as well. Okay? The transition takes place downstream first, okay? Not at the upstream section. Okay? And if you now plot the transition Reynolds numbers from the theory and experiments from different ways, dye stream, wall oscillations, pressure drop, and so on, now you see that's a very good match. Okay? So I'll end my talk here. This was the abstract that I put up in the beginning. What I had said was that fluid turbulence in the transition is probably the most importantly unsolved problem, more than a century after discovery. I tried to give you an idea of the distinction between laminar and turbulent flows and characteristics of turbulent flows, and why fluid turbulence is difficult to understand, but more importantly, essential for life as we know it. I showed you that in some cases we understand why the transition takes place. We still do not have a good understanding of the flow after transition, but we understand why the transition takes place and why there are routes to turbulence. But there are flows for which the transition is still not understood. The simpler flows, pipe flows, channel flows, and so on, we still do not understand even the transition to turbulence, why it takes place. Okay? And the reasons for that will be highlighted. And some of our work on understanding turbulence at small scales I discussed towards the end. There is a last line in the abstract which is not appearing here, and that is that the talk will be at the basic level accessible to all. So that is something that you have to tell me. Okay? I'd appreciate your feedback on that, and I'll be happy to answer any questions. Thank you. Yeah.
Sir, you were talking about Kolmorov's scaling at the beginning.
Huh.
So you say that smallest length scale goes by the order of Reynolds to the power minus 3/4. So what does that eta actually mean?
It is the smallest scale at which you have coherent motion of the fluid.
So is it like a smallest length scale of an AD?
Yeah, you can roughly think of it as the smallest length scale of an AD.
Okay.
More formally, it is the length scale at which the Reynolds number based upon the length scale and the velocity scale of the AD becomes 1. Okay.
So
So
both the inertial and the viscous
yeah.
terms would be
At the small scale, inertial and viscous terms are comparable. See, at the large scales, inertial terms are much larger than the viscous terms, which means that the energy production rate, the rate at which you're pumping in energy, is much larger than the dissipation rate due to viscosity. that is why it gets channeled into smaller and smaller scales, until at the smallest scale, the rate of production of energy at the large scale, the rate at which energy is pumped in at the large scale, is equal to the rate at which energy is dissipated by viscosity at that smallest scale. Okay, so the Reynolds number based upon that scale has to be 1. Okay, so that is the formal definition. Okay. Yeah, and that range increases as the Reynolds number increases R e power minus 3/4 or R e power plus 3/4. So if you have a 10 kilometer this thing, the Reynolds number is about 10 power 10, so 3/4 of that will be about 10 power 7.5. Okay. So based upon that, if you calculate the smaller scales, it turns out to be less than a millimeter, even though the large scale is kilometers in length. Okay. Yeah.
When we define Reynolds number, generally we use it as a ratio of the inertia force to viscous force. But if we go within the boundary layer,
Yeah.
say if there's a boundary layer over a flat plate, we write the equations from the Navier-Stokes when we come to the boundary layer equations, and if we do an order of magnitude analysis, we equate the inertia force to the viscous forces when we are going from the basically the Navier-Stokes equation to the boundary layer equation, which is a scaling analysis. So ideally, when we are scaling a boundary layer on a delta L scale, where delta is the boundary layer thickness and L is the flow dimension, we are getting a Reynolds number, say, on a flat plate of the order of 10 to the power 5, where we
2 into 10 power 5.
remains laminar.
Yeah.
But when we scale the problem,
Yes.
we say that both of them are of the same order.
Yeah. No. Yeah.
So the point is that when we are giving the definition of Reynolds number as the ratio of two forces, and the value comes to be of the order of 10 to the power 4 or 10 to the power 5 before transition.
Yeah.
So this whole concept of Reynolds number within a boundary layer,
Yeah.
do you think it requires a relook if it given in terms of
Yeah.
the ratio of two forces?
Yeah. So I had said that transition takes place typically when the Reynolds number is of the order of 10 power 3 or so. In the same boundary layer, right, if you scale the length by the streamwise length, then you get 2 into 10 power 5 as the transition Reynolds number. If you scale it by the boundary layer thickness at that location, it's about 10 power 3. Okay. So that's because the boundary layer thickness is the correct length scale there. Okay, that the boundary layer thickness is the distance over which the velocity varies from 0 to the free stream velocity. So the strain rate in the boundary layer is equal to the velocity divided by the boundary layer thickness, not the streamwise length. So if you do it that way, then it comes out roughly correctly. It will be about 10 power 3 or so.
But it doesn't come to be of the same order.
No, it won't come to be of the same order. The point is that, see, I said that the turbulent transition is discontinuous. I don't know if I had a figure there. Okay. I mean, that is still an open question. Is it 1:10 or whatever, right? What is the ratio? Okay. But if you actually look at a pipe flow, okay, I don't have that figure there, but if you plot the pressure drop versus the friction factor versus Reynolds number, there is a decrease, and then at some point there's a discontinuous change. Okay. That discontinuous change is because in the laminar flow, right, there were no small eddies. But in the turbulent flow, it spontaneously creates creates small scale structures. And because of that, the pressure changes discontinuously increases at that point. Okay, so for the same Reynolds number, you can have two different pressure drops. The pressure drop or the dissipation rate in the turbulent flow is actually much larger than the laminar flow. That is because it's creating small scale eddies, and the smallest scale Reynolds number is of order 1. Whereas that is not true for the laminar flow. Okay, so that's why that happens. That discontinuity happens. It happens for a flat plate as well. Okay, if you go from a laminar to turbulent flat plate, there's actually a discontinuity in the friction factor. That is because of the effect of the small scale eddies. Okay. Yeah.
So you have talked about the length scale, and so what about the time scale? Because that is also a very important parameter which will analyze the turbulence.
Yes. So actually, there's length scale, time scale, and velocity scale.
Velocity scale.
Okay. But two of them are related to the third one. Okay. So in the Kolmogorov equilibrium hypothesis, all three of these depend only on two parameters. That is the energy input rate per unit mass and the kinematic viscosity. Once you have that, you can just do simple dimensional analysis and get it. So I think the time scale for the smallest eddies is about RE power minus half times the time scale for the large flow. I think one is, and the third one is 1/4, I think. But all three of those are obtained on the same consideration. So the energy dissipation rate per unit mass, energy dissipation rate has dimensions of mass, length square T power minus 3. So per unit mass is length square T power minus 3. Kinematic viscosity is length square T inverse. Okay. So from those you can get only one length scale, one time scale. Okay. And so they're all related actually. Yeah. Okay.
What is the physical mechanism behind the transition Reynolds number being affected by elasticity? What really happens at the interface between the soft material and the fluid?
Yeah. So this is sort of it comes about because the strain rate is discontinuous at the surface, right? So because if I here, okay. So if you look at this one, for example, right, the strain rate in the fluid is finite. The strain rate in the solid is 0, right? So if I displace it a little bit, right, the velocity in the fluid is still 0 in the mean state. Velocity in the solid is slightly higher because the strain rate is non-zero here. So in the mean state, there's a velocity discontinuity at the interface. But the total velocity has to be continuous. So it has to generate a fluctuation. Okay? And that fluctuation, I mean, in all of these interface problems, there's some discontinuity in the base state, velocity or something. So when you displace the surface, there has to be a fluctuation contribution to maintain continuity, and that is the same mechanism. Electric fields also is the same mechanism. So it's some discontinuity at the surface. In this case, it's the strain rate, and in the earlier Kelvin-Helmholtz that I was talking about, there's actually a difference in velocity. When one fluid is moving at a finite velocity, the other one is stationary, then there's a difference in velocity between the two. So if you generate a fluctuation, on one side the velocity is higher, and the other side the velocity is lower. So you have to generate a fluctuation in order to maintain continuity. So that's
Is it something to do with flow over sand dunes?
also.
Suppose if you have a sand dune,
Yeah.
you have a similar situation.
Yes.
And therefore over sand dunes you have more turbulent flow than if it would be the sand
Yeah, sort of. Except that those flows are much higher Reynolds numbers. So typically you use the Bernoulli equation. Okay. So the Bernoulli equation, the cross section above the crest is actually lower than above the trough. Right. So the flow velocity is higher. So when the velocity is higher, because of Bernoulli equation, the pressure is lower. Okay. Pressure is higher at the troughs and pressure is lower at the crest, and that exerts a force that tends to amplify disturbances.
Is it similar to this type of flexibility?
Not in that sense. It is not similar because the discontinuity that we are talking about is the pressure discontinuity. In this case, it is the velocity discontinuity, strain rate discontinuity at the surface.
Yeah, in case of the transition strain, the non-model analysis are helpful to capture the
Yeah.
phenomena.
Yes. So non-modal analysis, you've been doing it for
In case of shear.
shear flows, right? Yeah. So in this particular case, we found out that, so we didn't do the non-modal analysis, but as best as we could see, the normal mode analysis and the experiments were agreeing. So there was no real requirement for a non-modal analysis. Okay. I mean, all these analysis, people do it when they're not able to get agreement. And as best as I know, the non-modal analysis only predicts that disturbances increase and then decrease again, right? I mean, it doesn't tell you about transition.
That is my question is that we are predicting something in the non-model analysis and we don't have experimental results.
Yeah.
So how can you make sure that these results are we are getting?
You have to do see. The problem with this is that I said that any disturbance can be separated into a series of modal disturbances. Now, the same is true for non-modal. Only thing is, if you want to get it from experiments, the disturbance in the experiments has to be the same as the eigenfunction you're using in the analysis. That is very, very difficult. Right? How do you tailor a disturbance across in such a way that it mimics the eigenfunction you're getting from the, okay? That is where the difficulty in experimental confirmation is. Okay? In any case, non-model analysis, ultimately the disturbance will decay, right? And it goes very high, but then ultimately in a long time it decays, right? So it doesn't tell you about transition to turbulence actually. It just tells you what is the amplification that will take place because of the projection of the velocity vectors of the eigen.
Some coherent type structures in the flow.
Yeah, I mean, coherent structures are basically the eigenfunctions you're getting, right? I mean, if you see something, you get an eigenfunction and then you call it a coherent structure. But the point is that you have to be able to put that disturbance in the experiment and then see what happens. Right? That is difficult. I mean, it's a good thing to try, but it's very difficult to do. These are all absolute instabilities. Because we did temporal stability analysis. There are convective instabilities also, but when you go to very low Reynolds numbers, right, in any way the convective term becomes small. So the dominant instabilities at low Reynolds numbers are actually absolute instabilities.
If there aren't any more questions, let's thank Dr. Kumaran for the talk.
Yeah, thank you. You can close this, right? Okay.
So, as a thankful gesture from the institute, we'd like to felicitate Professor Kumaran for the lecture. So, I request Professor Rajesh to hand over a memento and a shawl to the Professor Kumaran. There are some refreshments for all the audiences outside, so we can have